Today we're going to talk about how to actually solve an ordinary differential equation with a simple numerical method, which we'll call Euler's method. We'll also look at some examples, right? Compute them by hand, essentially. We'll also look at, this numerical method is a numerical method to approximate the solution, so it makes errors, and we'll look at how the errors look like. We'll look at the multivariate version of the Euler's method. It's important, for example, for an epidemiology kind of example, and we'll also look at the Matlab implementation. So let's jump it right into Euler's method, right? So once again, let's restate our ODE, right? And let's say that our ODE will be given by y prime. Let's make it a variable function of t, and you're given this equation, which will be a generic f here on this right-hand side. So I'll just write f of y of t. We saw some examples in the previous class, right? And let's assume that it's an initial value problem, so we're also given the initial conditions, and for the time being, we can call this y of t0 called y naught, and this is given, right? So in fact, these two things are given, and this is what we call an ordinary differential equation given an initial value, so also called an initial value problem. And the goal here, let's state the goal kind of in a simple form so we understand what we're doing, is compute the value of y at t0, right, which is already given, at y at t1, y of t2, and so on, however many we would like. So, right, this is the goal. So, for example, we can determine that ti, for example, will be I times h, for example, right? So in this case, for example, t0 would be 0, t1 would be h, t2 would be 2h, and so on, right? So we can choose a small step size. We call this h small step size, which will be fixed for now. Later we'll look at other things. So here is Euler's method. It's essentially an application of the Taylor series. So we know the Taylor series for y evaluated some value h, right? So t plus h, h displaced from t, is given by y of t plus h y prime of t plus, other terms, but I'll abbreviate this here, that the largest of which will be order h squared, like we're assuming h is a small time step. So, and we're going to ignore this. We're going to assume that we choose h small enough that this term, order h squared, it's even smaller, so it's going to be negligent, negligible. The error that we'll see in this method will be negligible, right? So the whole goal here is that we start from this given, y of t0, and since this is given, we can plug t0 here and y of t0 here, right? So let's do this here, right? That y prime is given, yt plus h then becomes y of t plus h f t y of t. So that's given. And that's it. This is Euler's method. That's all we need to remember for now about Euler's method. So with this formula in mind, let's look at this algorithm. Right, so the start, step 0. Start from the given values that you have, t and y of t0, which is we call y naught, right? And then step 1, compute t1, which is going to be 1 times h in this case, and then compute y of t1, And this will be given by Euler's method, the formula. And we know all the parts, so I'll just write this down here below. This is going to be equal to y of t0 plus h, and I can plug in what I know. This is also given in the problem, right? So I'll just say plus h times f at t0, y of t0. These things are given. Step 2, let's do one more step. Now we compute t2, which is going to be t1 plus h, right? Or 2 times h. And then compute y of t2 to be equal to y. It's a same application of the previous Taylor series, plus h f t1 y of t1. And we repeat this as many times as we would like until we get to the solution for the values of t that we would like to have, right? So this is a very short, very simple explanation of what Euler's method is all about. It's just an algorithm. It's a numerical algorithm that uses the Taylor series formula, takes essentially the first order expansion of Taylor series, and then starts from a given value and computes the next value, always with the same formula, right? It's a recursive kind of formula. So so let's see how this looks like in a more specific setting. So let's look at the specific initial value problem, right? The setup of the problem is given here. This is a compartment model in this case here, right? And we're going to assume that the k in is given by this and the k out is given by this, and we have initial values over here. So we have the whole problem set up, and as we remember from our modeling, our video on our initial video on ODEs, right? So this compartment model is essentially k in minus k out. And so in this case, for this specific example, we have dc dt, which will be equal to 100 over t minus 0.1 times c, right? And all we're going to do next is apply Euler's method, right, which is essentially a Taylor series, which will be c of t plus f of t c of t times h, right? So this is what we're going to do next. And so let's look at this example of what happened here next. And so just to be complete, we have the formulas in front of us. I'll also write this here. C of ti plus h will be equal to c ti plus, and I'm gonna go ahead and plug in this for the CDT or f, right? So I'll plug it in here, and that's going to be 100 over ti minus 0.1 c of ti times h, right? This is our f, which, you know, one thing that I forgot to discuss here is this notation here, right? So, oh, by the way, so Euler's method is given over here, right? But oftentimes you'll see it written in this form. And this form, essentially, it's the same thing. We're just plugging in, calling a phi, and plugging in a phi in here. And the reason for doing this is that we'll see other methods that are slightly different from Euler's method before. But if we call this incremental term here a phi instead of the given f from the ODE, then we can plug in different phis here, right? And the different phis will essentially correspond to essentially taking higher order terms of this Taylor series. So the approximations will get better and better, right? But this is a notation that we'll often see. And the other thing you'll note here that this y I plus 1 here is, instead of writing, you know, y of ti, so this is going to be y of ti plus 1, right? So there's no real sense in keep writing the ti here, because the t, it's implicit, right? So all we care about in the computer, in the programming, is actually the I plus 1 for the array, right? As far as bookkeeping. So so that's the reason, and this is why in this case for Euler's method we call this the phi, right? So let's apply this solution, the Euler methods to solving this this particular compartment model. So the first iteration, right, iteration 1, is essentially given, right? We're given a starting point of 3, time equals 3, and we're given the value of a function at that time, so that's given. With these two things, we can plug them in here, right? So we plug t equals 3 in here, and c here 3, to compute then, this will be the phi that we'll need to compute the next value of the formula, right? So here's phi, we compute that, and in this case it happens to be 23.3. We then compute, right, so in this case we're also choosing a particular h, step size 2, so 3 plus 2 is 5, so the next one will be 5, right? And which in this case gives us the next update, right? So instead of t1 here we have now t2, right? So the next value of the function, so we started a value of function 100, now it's 146. Let's do another iteration, right? Iteration 2, now we start from here, that's given, we have that also given. Now we compute the updated for phi here, that's 5.3, right? And we can go ahead and move to the next time sample, but the function at this particular value, at y at t equals 5, would be given to by 147, right? So it's a very simple formula to keep applying, and computers are ideal because they can turn these simple formulas into a less tedious task. The computer will do essentially all the work for you. So, up till now we have been talking about a single equation, right? A single function y of t that we would like to discover, but we've also talked about systems of ODEs before, right? The sets of ODEs. For example, the SIR model for epidemiology requires 3 equations, right? So S, I, and R for susceptible, infected, and recovered. This was an example covered in the previous video. And right, so here are the functions for S, I, and R. This is Taylor's Euler's method applied to each of them individually, right? So now we can talk about solving a vector function, right? So where we have, for example, we can call P of t to be our vector of S of t, I of t, and R of t. We can put all these 3 values into a vector, which we call vector P of t, right? Using our linear algebra notation that we defined from our previous unit in this course. We compute our phi of t for Euler's method. Now this will also be a vector, right? So this will be ds dt, di dt, and dr dt. So we concatenate these 3 values into a vector, and then we essentially compute the Euler method on the vector of 3 functions that we'd like to solve. So t plus h will be given by p of t plus this vector phi times rh, right? And we apply the same formula. We can do this at home, but right, so we have then, we're looking for the solution for 3 things, right? This is a function of t, this is s, this is going to be a function of t, this is going to be the infected, and this is going to be the recovered, or the recovered, or the immune t, right? So in S, everybody will be susceptible at first, and hopefully, the susceptible folks will go down, right? So you start here, and then the curve will start going down. The infected initially will be 0, but then you'll start coming up, and the recovery, initially will be 0, but then also will coming up. And so this is what you're going to do here also. Start from this time step here, and compute the next estimate, right? Maybe it runs there. Start from this time step, you go there, and you trace out the whole curve. So let's talk a little bit about the error estimates for Euler's method, right? Which is the simple method. So all we're doing with Euler's method is we're given some initial time vector. In this case, it's an x variable, right? And we're given this guy. And let's pretend that this curve here is the actual solution, right? The true solution. And as we just saw, Euler's method, all it does is it takes this value and takes the slope, and then takes a step of size h along that direction. So it actually pretends that this function is a constant within that small region. And you can see that if we take h to be big enough, right, and we follow along the straight line here, there'll be an error, right? This should be the true value for the next step, but we computed this from Euler's method. So, right, this is the step we took, but we made an error, and this is the size of the error. So let's look at this and see how it really looks like, right? So the ODE statement, as before, is y prime of t will be given by some f, right? Different f for different problems, y of t. Right? And essentially what we did was that we used Taylor series to compute, right? And by the way, we have y of t naught equals y naught given, right? So this is given. And then we said, okay, y at some displaced value h from t naught, what's the formula for that? That's where we plug in Taylor series. And that's going to be y of t naught plus y prime of t naught times h. This is going to be divided by 1 factorial, right? So I'm just using the formula for, and then y double prime of t naught times h squared by 2 factorial plus other terms, right? And if we recall what we did before, we says, okay, let's pretend that h small is small enough that this is good enough. So this is Euler's method, takes only these values. Right? So we can say that for one iteration, Euler methods makes an error, which is essentially this remaining value. The largest term here will be order h squared, because the size of this remaining terms, the largest will be, roughly speaking, order of h squared. But then remember that we are going to repeat this for many values, because we're going to choose a small h. We're going to repeat this many times to get all the samples of t that we would like for through the entire function, or at least the region where we're interested for that function. So we're going to repeat this many times. So and each time we're going to be making an error of order h squared, right? So once you accumulate many errors like that, the global error, the total error, right? Let's call this total. Sometimes it's called the global error. Will be something a little bit bigger than h squared, and you'll be given by t t minus t naught, right? The total interval divided by h times h squared. So the total error will be essentially order h, which means that the error in the after many iterations will not be as small as h squared, but it will be essentially order h, right? So this is essentially the number of time steps between the final value of t that we like and the initial one. So so let's look at this system once again. And by the way, this system can be solved by this exponential integral function here, this e int. We're not going to get into that, and the reason why we're actually solving these things numerically so that we don't have to go through very complicated steps. Sometimes we can even get a solution and express it this way. Sometimes the equations are complicated enough that we can't even find a solution. From an engineer, we don't need this. From the engineering point of view, we can do just as well by computing a very good approximation to the solution like this with Euler's method. But in this case, right, just if we want to know, this EI here is essentially the integral from let's say t to infinity of e to the minus t. So let's say x, right? So x, my bad here, because t we used as the integration variable there, so I have to, let's use x here. X over t dt. Right, so we have an expression. In this case, we're lucky we know the expression for the true solution. So let's use Euler's method programmed by a computer with different step sizes so that you can see the size of the error as a function of the step size. Right, so here's this true solution. It's given by this black curve here. I'll highlight it here once, and that's the true solution. If we choose a large step size, Euler's method will have a very large error. In this case, it kind of recovered and went back close to the original function, but that was kind of an accident for this particular example, right? It doesn't always come out this way. But the point here is that this error reduces dramatically as essentially roughly at the same rate that we reduce h. So a smaller h, so for example, h equals 5, step size 5, you can see this function doesn't stray as far from the actual solution than the h equals 10 was. We can reduce it further to h equals 5, h equals 2, h equals 1, right? So, and we get closer and closer. We can go from h to be 0.5, 0.2, 0.1, 0.0001. And you know, the computer is your friend here. You have very fast CPUs, and for simple examples like here, you know, you can spend an extra second and be double sure that you're getting a very good approximation to the solution. So how does all of this look like in Matlab? So it's very simple to implement Euler's method in Matlab. Here, let's begin. We define a variable for the h, step size, right? And then we define our t vector. We're going to compute our function c at these values, so 3, 8, right? 8, 13, all the way to 50. So we create an array to store all the values here. We start C1 is given by our initial value, right? Where is it stated? Somewhere. It's somewhere over here, right? So we're using this this problem here as the example, right? So let's go back to the problem, right? So here's initial value for that's given, and then for this iteration variable, right? So we already have the iteration 1 that's given. So for 2 and to the number of elements in the vector t, compute dc dt, right? This is just name of a variable. That's the formula given in the ODE. And then we can go to the second iteration. We take the first value and, you know, the step size. We could have also just plugged in h here, right? So that works the same, times that, and we store that in the new value. And this is how we plot it. So here we also plot the original solution, and here is the solution with Euler methods time step 5, although actually this plot was for 10. I apologize, should have changed to 5. So there you have it, right? Very few, less than 10 lines of code. You can implement the solution of an ODE like this and plot it in Matlab, and it works pretty well. So you would do here, of course, is you would choose an h to be, let's say, 0.001, and you have a very, very good solution.